Good morning or good afternoon, everyone. My name is Ranjit, Senior Application Engineer with Mirabilis Design. I would like to welcome you all for today's webinar, Engaging Students and Researchers of Embedded System Design for System-Level Modeling and Simulation. The major reason for taking up this webinar is to provide an overview of how exactly VisualSim can help in system-level modeling and help students to understand the concepts of complex system architectures, and also at the same time how professors can actually utilize VisualSim to explain complex system architectural concepts to students and provide hands-on experience on understanding various different technologies and complex concepts itself. So before getting started with today's webinar, I would like to go over a few items. You can see a window something like this on your right-hand side of your desktop. Please feel free to post in your questions in the chat window. We have people in standby. They will be answering all your questions. And also I'll be taking up these questions in between as well. And also I'll be taking these questions if I can't complete at the end of the presentation as well. So we would love to hear from you. Please feel free to post in your questions, and I hope you enjoy this webinar. So here is a quick outline to today's webinar. I will be starting off with answering why exactly system level modeling is required. So what are the benefits that a user, for example, a student or maybe a designer is going to get out of this system level modeling, and when exactly they will have to start off this system level modeling, and what are the kind of analysis or the kind of inputs or the outputs that they can get out of this approach itself. And also I'll be going over how a complex system architecture, it could be an avionics system, or it could be a radar system platform, or it could be a kind of semiconductor, maybe an SoC or memory subsystem itself. How one can architect such systems all the way from your complete system platform into a kind of subsystem level or kind of micro level architectural uh, design itself, considering power and performance characteristics to make sure that the requirements, whatever defined, are meeting at the end of this uh, once you have selected the architecture itself. I'll be going over a few demo examples as well in this webinar that talks about selection of an IoT system platform itself, or how exactly I can define my applications to meet the deadlines that are defined for avionics applications, or it could be a kind of selection of a architecture or hardware software partitioning for a multimedia application itself. And also at the end of this webinar, I'll be providing you the details on what are the kind of offerings that we provide for our students and professors to get started with VisualSim in their curriculum or for the project work or something like that as well. So for those of you who has not heard about Mirabilis Design, we are a Sunnyvale, California-based systems engineering company, and we have offices in China, Japan, Czech Republic, and India as well. And we have over 50 plus customers all the way from different domains, all the way from semiconductors to consumer electronics, avionics, automotive, and high performance computing system space. And also we are working very closely with a lot of universities as well. Many people are actually using VisualSim as part of their curriculum, and also research professors actually using it for next generation technology explorations and things like that as well. The whole idea of using VisualSim Architect is to make sure that the selected architecture is going to meet all your requirements in terms of power, performance, reliability, and functional correctness. So why exactly the system level modeling is required? So if you consider any system architecture that you're seeing in day-to-day life, all these systems are kind of very compact systems, and you're trying to run lots and lots of applications on these target platforms. And these kind of running multiple tasks on the same platform or with limited amount of resources tend to cause challenges, or in terms of you will actually have a lot of contention for resources as well. And that actually causes challenges in terms of end-to-end latencies or performance of your systems, or your system instead of completing a particular task in a given timing deadline, it may actually take another 25% more time to complete that particular task itself. So in order to identify what is really going on, or what really happens if you go with a particular set of architecture, or a kind of defined set of behavior sequences, so if you have a very simple application, or if the application is fully pipelined with no contention of resources, then you can simply add up those delays and try to understand what is going to be the end-to-end delay using simple spreadsheet. But if you actually have more and more applications running on the platform, you will actually have dependencies there, you will actually have contention for resources itself, and those contention will actually cause additional latencies or additional timing delays associated with that as well. And these additional delays will actually cause unpredictable system response time as well. To give you an idea how exactly a simulation model of this particular complex uh, scenario would look like, I would like to go to VisualSim Architect right now. And I hope you can see my screen here. And this is VisualSim Architect modeling and simulation environment. And here I have defined my hardware architecture as well as my software behavior flow for two applications in my case over here. And in the hardware architecture, I have two CPUs and a DSP and an IO. IO could be an USB or an Ethernet that are connected across a bus and a bus bridge. And each resources are running on its own different set of clock speeds. And at the bottom, what I have over here is I have defined my application as a sequence of tasks that are running on the platform. For example, the way how it works is you actually receive the transaction from your IO interface and then go across bus to CPU and do some processing over there, and go across bus 1 to bridge, bus 2 to DSP and do some processing over there, and go back to IO. So that gives you, or that is going to be one definition for the behavioral activity of a particular task itself. So the amount of time that it takes to go across all these different resources will actually give you the end-to-end latency for that particular task itself. So you might be expecting this particular task to be completed within a specific time period. A simulation run will actually provide you details on how long or how much time that particular task is taking to execute on the target platform that you have. For example, if you look at this particular graph over here, I have captured the software task latency for application 2. X-axis defines my simulation time, how long I'm running the simulation, and Y-axis gives me the end-to-end latency. In this case, the maximum latency that I have received or I have captured over here is just before or just below 1.5 microseconds over here. And if you look at the statistics that we capture, the CPU 1 is utilized about 92%, whereas CPU 2 is utilized about 55%. So this actually gives you an understanding or kind of information saying that you are using two CPUs, but one CPU itself is utilized over 90%, and you can actually move around 20% tasks from CPU 1 to CPU 2, then you will be actually having a balancing over there, and the selected platform would actually be sufficient for the current set of applications what you're going to run with. So if you want to go with a kind of maybe after 5 years you might be interested in running 10 more applications on the same platform, you would actually end up configuring these different resources to meet all those requirements by running these simulations runs itself. Okay, and at this point I would like to go and make a minor change over here. For example, earlier I was running my bus 2 at 200 megahertz. I'm running now at 400 megahertz. And increasing that particular clock speed, I'm actually expecting the latency to come down, and I can see that reduced latency over here. Most of the tasks are being completed under 1.25, but there are some tasks that are actually going above 1.5 milliseconds, oh sorry, microseconds. So earlier case, the maximum latency was below 1.5, but with the increased bus speed, I'm actually having kind of unpredictable system response time over here. You're actually, the tasks are running much slower now. The problem could be your bus is running or providing too many transactions or to the processor, but processor is not fast enough to process all these instructions. So you will have to go with a higher configuration of the processor, or you will have to go and try to understand or modify the topology of the system itself to meet your requirements at the end of the architectural decisions. So these kind of inputs will actually provide a lot of information to the designer. So when they are actually starting off with, for example, if this particular model is constructed within a couple of hours, so that is the kind of capability that a designer is going to get out of it. And in addition to that, you need to consider the factors such as power consumption and latency and availability of the resources itself. So you can't really make your architectural decisions purely on the performance side or purely on the basis of power consumption, but you will have to combine these two factors and generate an optimal system architecture that meets your both performance as well as power requirements as well. And also, if you have any kind of hard real-time applications running on the platform, then you will have to make sure that if you are going with a particular architecture, the timing deadline for the tasks that I'm running are meeting and the requirements are met. So these are the kind of problems that you need to consider while architecting a system platform. And these factors are these are the characteristics, whatever I just talked about, can be captured only with the help of a system level modeling and simulation. And availability of these different factors or the kind of values will actually provide a lot of inputs or the kind of confidence to the selected platform itself. So the kind of problems that you could anticipate after implementation will actually reduce in a greater number. So considering these factors, we have assembled our tool, VisualSim Architect, and the way how you construct simulation models is purely using a graphical format. So the environment itself is completely graphical and hierarchical, which means you don't really have to spend a lot of time on learning a new language or learning a new script or something like that. Instead, you can simply drag and drop the library component that we provide, and you configure it based on your requirements. And also the libraries that we provide helps you to model the hardware architectural elements or application behavior sequences or defining an interface itself or how exactly an RTOS is going to run on the RTOS itself. And with the help of this different set of library blocks, you can conduct varieties of analysis all the way from performance analysis, hardware software partitioning, power analysis, and by looking at these different reports, you can select upon a particular architectural element itself. And these library blocks that we offer are provided in multiple abstraction levels. We call it as statistical level and cycle accurate level. So based on the level of details that you need, or based on the level of accuracy that you need, you can select these library blocks and start modeling immediately. So as I mentioned, please feel free to post in your questions if you have any. Here's a quick view about our the list of libraries that we provide as part of the package, all the way from traffic generations to processor libraries and Xilinx FPGA libraries, board level and networking and all that. And all these libraries are completely configurable. And also, interestingly, most of the libraries are provided with at least 5 to 10 demo examples, which makes it very easy for any user, for example, for a student to get started with these models and try to understand how exactly a particular technology is going to work with a full system environment. So for the student itself, we provide, student is going to utilize VisualSim to perform varieties of practical lab experiments with VisualSim, and they will actually try to understand the theories that they studied about. For example, it could be schedulers, or it could be an arbitration algorithms, or it could be the flow control algorithm itself, or it could be a single core platform versus a multi-core platform itself, how exactly they would look like in a real scenarios and all that. To give you a quick understanding of how simple the models can be, to explain the concepts, here is a, I hope you can see it. So here is a model that actually go over uh, exploring scheduling algorithms itself. For example, in this case, what I have over here is I have a scheduling resource, which means this includes a scheduler plus a processing resource in it. And I have defined multiple software tasks that are going to run on the same resource that I have here. And these resources, or these tasks, can actually arrive at the same time, and these tasks can have their own set of priorities as well. For example, if I double click on this mapper block over here, I have defined this particular task as task number 1, and I have provided the priority as 1 here. And this task is going to run on the target resource for about 3 seconds. Similarly, the task 2 is having a priority of 2, and it is going to run for 3 seconds. Similarly, for the third one, I have the priority as 3, and it is going to run for 3 seconds. So in this case, what we have over here is my third task is actually having highest priority. So in our case, we consider higher the number, higher the priority. So if I go ahead and before that, and if we look at the scheduling resource here, the scheduler type, I have set this to first come, first serve. So based on which task arrives first, I'm actually, or this particular resource will actually serve that task itself. So if I look at this particular graph here, so what you can notice over here is this is my task 1, which is actually completing its processing time of about 3 seconds here. And I have my task 2 and I have my task 3. So as task 1 arrived at first, this was actually served first, and later task 2 and later task 3 has arrived first. So what I'm going to do at this particular point is I'm going to change this scheduler type from first come first serve to a preemption based. As we have already provided the priorities for these different tasks, I'm going to run this particular model again. And as I can see here, I'm going to zoom into a particular portion here. So what I can see here is this is my task 1. As soon as it finishes 2 seconds, the next priority task, which is actually task 2, has arrived, and that the task 1 was preempted, and the highest priority task was actually served. And later, task 2 actually elapsed for 2 seconds, and again there was a higher priority task, which is task 3, and that was actually considered over here. Similarly, once my task 3 execution is over, the next highest priority task, which is actually task 2, was actually taken from the preemption queue, and it was taken for processing itself. So this is a kind of very simple way to explain how exactly a preemption-based scheduler would work, or something like that. Similarly, you can actually set this to varieties of other options. For example, you can mention the round robin, or it could be your own scheduling algorithm itself. You can explain with the help of these different library blocks itself. Okay. So, and in addition to that, for example, if I'm talking about a flow control algorithm, so in this case, what I have over here is this is an X on X of flow control algorithm model. So in this case, what I have over here is I have two ingress queues on the left-hand side. I have an egress queue on the right-hand side over here. And in between, I have these X on and X off queues here. The way how this ingress queue works is ingress queue, this particular algorithm, what I have written, will actually keep on looking for the availability of the egress queue resources. So if egress queue is available, then this ingress queue will actually start sending the transaction out. For example, until it reaches the threshold limit for or something like that. So this can be, in this case, this is a kind of round robin based. So we keep on sending the transaction out of it. And this could be a credit-based flow control algorithm as well, you can mention. So the way how it works is you can actually utilize these basic building blocks that are defined in VisualSim to define the kind of algorithms that you want to implement in your academics as well. So if I go ahead and run the model for this, in this case, I'm actually trying to understand what is my end-to-end latency from my ingress queue to egress queue itself. And also I'm trying to understand what is the buffer occupancy in my resources as well. For example, how many packets of information that I need to store in the buffer. So I need to store a maximum of about 33 packets must be stored in my buffer, and I need to make sure that I have sufficient space provided to save those packet information as well. Okay, so at this point I would like to go back to the presentation. And similarly, you can actually model the network architectures as well, and you can model and explore complex system architectures such as high-performance computing systems or NVM-based non-volatile memory architectures and things like that as well. The whole idea is to explore the concepts that you learn in the theory classes and make sure that you understand how exactly these concepts are implemented in the system level or in a real system. Okay, so one more example that I wanted to show here was to understand how exactly a network model would look like, or what happens if a particular network link breaks down and what is the impact of that on the rest of my system. In this case, what I'm doing over here is I'm actually removing the network link between node 3 to node 5 and adding it back after some time period. So running the simulation over here, it's actually providing me details on what is the impact of removing and adding a network link back onto the system network, and what is the impact of that on my end-to-end latency itself. Okay, so for the professors, we actually provide a complete embedded system curriculum along with the training materials and class notes and laboratory demo examples as well. And they can actually utilize VisualSim to publish research papers and share these simulation models with other professors or other industry people to actually look at the kind of research work that you have conducted. And also you can share these simulation models and utilize VisualSim to give a kind of visual education for emerging topics as well. For example, the topics such as rapid IO, or it could be some other new technologies that are coming in as part of the system architectures in the later stages. So in terms of the application challenges that are being addressed with VisualSim, it could be all the way from designing a radar system that meets all the performance requirements and kind of allocation of the buffers and things like that as well. And also it could be a kind of creating a communication network that supports hundreds of thousands of nodes, in which case you might be having currently about 10 or 20 number of nodes in your scenario. It could be a kind of creation of or creating an IoT device architecture which can sustain about 10 years of battery life itself. So how exactly you can architect your IoT system platform to meet your power requirements at that particular time period. And apart from that, you could actually design a multimedia SoC platform to meet your performance versus power trade-off to meet all the requirements such as the macro blocks processing and things like that as well. So I'd like to go over to demo example right now to give you a few ideas how exactly it would look like. For example, in this case, we have a 3G IMT 2000 TCP/UDP router design over here. And in this case, I have defined my behavior flow over here in which you have your IP streams coming in and you have your packet headers and packet data and you have your routing of the packets and things like that. And also we have the VxWorks background processing running as well. And with regards to the hardware architecture, we have defined in this hierarchical block over here, I have processors such as 8260 and MPC 750. And also we have the architectural resources such as memories, caches, and uh, physical layers and things like that as well. So in this scenario, what exactly we are trying to explore is we have provided a certain set of parameters over here, and these parameters would actually help you to kind of configure the system platform or understand a different set of configurations and different set of performance reports that you could get out of it. In this case, what we have here is initially I have about 100 users, and yeah, in this case, I have 100 users, and what else we have here is we have the packet minimum number of bytes as 200 bytes and maximum of 1,500. And in addition to that, what we have here is user kilobytes as well. How much a particular user is requesting from that particular resources itself. So what I'm going to do at this point is I'm going to run the simulation over here. And what we're trying to do here is we are trying to understand the input throughput versus output throughput and trying to understand if the output is matching my requirements. So if I see over here is my maximum, mean, and standard deviation throughput details are quite similar. Actually, my output throughput is a little bit less compared to my input throughput over here. So that actually tells you that you will have to kind of either run your processing resources at a higher clock speed so that the processing gets completed quickly, and that will provide sufficient space for the other users to actually request the data and things like that as well. So at this point, what I'm going to do is I'm going to increase the total number of users from 100 to 200 and trying to understand what would be the kind of impact that it would make on the throughput of the system platform itself. If you see over here is the maximum input throughput that I'm getting over here is close to 17 megabytes per second, whereas the output throughput I'm actually getting only about 15.12 or something like that. So that is my maximum throughput that I can actually achieve. So that actually tells you that there are a lot of packets that are being dropped off, and you need to address these problems as quickly as possible. For example, you would actually increase the clock speed of the processes that you're running. I'm going to make this to from 133 through 233. I'm going to run this model again and trying to see what is the impact that it is going to make. As you can see over here is my output throughput actually improved significantly at this particular timestamp after increasing the clock speed. So similarly, you can change these remaining parameters based on the details that you have with you and arrive at optimal architecture that meets all your requirements. So there is actually a question on does your software runs on Windows laptops? Yes. So we support Windows, Linux, Mac, and we run on all the PCs, and we just need minimum configurations itself. So in addition to a IoT system platform that I talked about, for example, in this case, what I have here is a single IoT device in which I have a photovoltaic cell that keeps on generating the power from my battery, and I have a rechargeable battery over here, and I have these components of that particular IoT device itself. I have my sensors, interfaces, MCUs, accelerators, and transceiver modules as well. And also I have defined my workloads and use cases as well. For example, the way how you are utilizing these different processing resources or interfaces itself. And for the photovoltaic cell, what we have over here is we have this a photovoltaic cell powered generator. So in this case, what we have here is we have these different profiles for different seasons. For example, for summer, winter, or spring, or autumn seasons. So for different seasons, we have actually defined the availability of the power itself. For example, in this case, if you look over here, between 11 o'clock to 3 o'clock, a maximum of about 60% power will be generated in autumn season. So this is one scenario that we have defined over here. Similarly for the other profiles as well. And this particular model is being simulated for a real-time 1 year of time period. And if I go ahead and run the model, the kind of reports that I'm actually capturing over here is trying to understand my battery charge and discharge cycles, and trying to understand the life of the battery itself, the kind of degradation of the battery life. And also I'm trying to understand the lifetime energy consumption of the full system over the simulation time. For example, for 1 year period, what is the maximum power consumption that I have actually considered. For example, in this case, if you see here, as soon as it is actually charging the system, you can actually see a kind of sudden drop in the battery life over here. The reason is while charging your battery, we are considering like the battery life will be actually degraded in certain number. Okay, so in addition to that, we are actually generating the latencies for different use cases and tasks that I'm running on the platform as well. So what is the maximum latency, or what is the mean latency that I'm actually getting out of it? Okay, so for a period of 1 year, we have actually identified that about after running or after using your device for 1 year, the battery life of the selected battery is dropped around 67% over here. So this will actually give you an information on whether I can go with this particular battery for my requirement, or I need to go with a different set of batteries. And also we have other details such as power consumption of individual components as well. For example, in this case, we are capturing what is the power consumption or average power consumption of my accelerator. Or it could be my average power consumption of my MCU itself. And also we are providing cumulative power consumption in joules as well. So these informations will actually provide you details on whether a particular component is consuming too much power, and if you have identified that particular scenario, you can actually introduce a power gating algorithm to make sure that that particular device is not consuming more power than what you are expecting. Okay, and in addition to that, one of the other example that I wanted to show today is hardware software partitioning and making sure that power performance trade-off is going to meet your requirements. In this case, what we have here is a multimedia system platform with processor and accelerator, Axibus, and memory subsystems over here. And at the bottom over here, I have my application sequence defined for a image processing platform. So in this case, I have my image sensors, and I have this read frame, decode frame, video post-processing, rendering, format conversions, and rotate frame, and things like that. So in this scenario, or in this model, we are actually expecting about 13,000 macro blocks being processed within 20 milliseconds of time, and power consumption of my system should not go above 1 watt of power. So that is a kind of high-level requirement of my system over here. And initially, we are running all these different tasks on the ARM subsystem, which means considering the partition as a software part of the system itself. I'm going to run this particular model, and we are actually generating the reports again to understand what is the macro blocks processing time that I'm getting, and what is the average power consumption of my complete platform itself. For example, my requirement was power consumption should not go above 1 watt of power. I can see here that I am meeting my power requirements over here. So because power consumption is under 1 watt of power. So if I look at the performance wise, I was actually expecting about 13,000 macro blocks being processed, whereas in this case, I'm actually getting only about 6,600 macro blocks being processed. So that actually tells you that performance is very poor, whereas power consumption is good. But this is not going to work for you, and you will have to change the architecture to make sure that performance is going to meet all your requirements. So we actually looked at the reports that we generate out of this tool. For example, we looked at the utilization of the memories and the stall time associated with the processor itself, and utilization of the memories and throughput of the different resources and all that. We identified that the rotate frame is actually taking more CPU cycles than expected, and what we did was we actually moved this particular rotate frame from ARM processor to a dedicated hardware accelerator. So I'm going to change this particular parameter over here to move this rotate frame from ARM subsystem to a hardware accelerator. I'm going to run the model again to understand whether this is going to meet my requirements in terms of performance versus power. So if I again look at the same reports that I was looking at, so here you can actually see here that average power consumption is actually quite bad. So I was expecting power consumption should be under 1 watt, but it is going close to 1.5 watts of power. Whereas macro blocks processing is very good. I'm actually getting about 14,600 macro blocks being processed, but power consumption is very poor, and the device may not last longer. And if you look at the power consumption of an individual device, I can see here my hardware engine is actually consuming more than 35% of my total power consumption, which is close to about 1 milliwatt of power is actually being utilized by the hardware engine itself. This actually tells you that the hardware engine is consuming more than what you are expecting. And if you look at the activity of that particular hardware engine block, we can see here that whether you have running something on the hardware engine or not, it is always in on state all the time. So you can actually introduce a power gating algorithm to make sure that if you have nothing running on the hardware engine, you can shut it down and bring it back whenever it is required. So that is a kind of third architectural decisions that you made with this architectural or system level block now. So if I go ahead and look at the activity of the hardware engine, I can see here that the hardware engine is actually active for a very shorter time period. As soon as it finishes, it actually sends to a kind of standby state or wait state. And also I can see here my average power consumption dropped back to under 1 watt of power. And looking at the performance wise, Performance dropped about 10%, but it is still meeting our requirement with about 13,000 macro blocks being processed. And if I look at the power consumption of my hardware engine, it is actually utilizing only about 1% of the total power, whereas earlier case it was consuming more than 30% of power. So these kind of problems and the kind of challenges can be addressed very quickly and very easily. And also these provides a lot of information to the implementation uh, people as well, so they can make the right decisions while designing or while working with the implementation level. Okay. So kind of when we looked at all these different examples, the kind of challenges that we address over here is to kind of have a balance between hardware architecture, kind of partitioning between hardware and software to meet your performance and power requirements. And also you can size the platform to actually process the tasks, whatever you're trying to run on the target platform. And also you can try to reduce the power consumption by looking at the performance and other factors as well. And in addition to that, if you have multi-core system platforms, it'll actually provide you information on how can I distribute my tasks between multiple processor core. And if you have a processor plus FPGA and an ASIC, so you can actually utilize to understand how can I distribute these tasks between multiple processing resources to get a better performance and meet the requirements that are defined. So here's a simple sample model in which I'm just trying to show you the kind of hardware architecture and the behavior flow. Both will be actually captured in the same environment, and you don't really have to do it in two different architectural or two different environments or something like that. So once your modeling work is over and exploration work is over, you can actually export these models to an HTML file and with the Java runnables. So in this case, what you're seeing over here is actually a model that is coming out of the web browser. And also you can download an executable version of the model uh, that you might be interested in sharing with some other people. So they don't really have to install the software. They can run the model, or maybe I'll show you that how exactly it would look like. So here is the model that I was talking about, and you would actually export this particular model along with the documentation, whatever you have. In this case, we have very minimal, but it could be a complete detailed documentation of the design and analysis. And these blocks are something like you can, once you hover your mouse over these blocks, it will actually provide you the parameters associated with all these blocks as well. And also if you launch these particular Java files, so what it really happens over here is you will actually run or open these simulation models right from the web browser, and you don't really have to have the software installed on the PC itself. So the user will actually uh, can conduct varieties of analysis by changing the parameter and changing the configurations, or maybe inserting some other additional use cases to the model and trying to understand how exactly the system platform is going to meet the requirements whatever you are expecting. So it is going to take a few seconds to load up. So if you see over here, this is actually the model that came out right from the web browser that you can see over here at the top. And I can change the parameters by double clicking on these different parameters. For example, I can change this parameter values, and I can run the simulations and save these simulation reports and into your local machines and utilize it for further analysis as well. And also we have additional demo example templates as well, which are available right here. You can actually go ahead and open any of these different models or download the models and things like that as well. Okay. So with regards to the offerings that we provide, we actually provide uh, free licenses or the licenses for the class itself, for the classroom use, a maximum of about 50 licenses we provide. And also in addition to that, we provide learning materials as well, including slides and documentations and demo examples. And we provide, in addition to that, we provide technical support as well. So if you come across any questions or any problems, you can always reach us. So we provide a full-fledged support there. And also we provide you a kind of facility to export all these models that you work with to a secured server, and you can share these simulation models with other people or other team. They may be sitting somewhere else in the world. So this is about today's webinar, and now the session is open for questions and answers. Please feel free to post in your questions.